Chapter 4 is all about vectors and vector spaces. So we're going to start out Chapter 4 with a brief review of vectors. Then we're going to get into the definition of a vector space. What is a vector space? We're going to show that there's a set of 10 axioms that must be satisfied in order to have a vector space. And then we're going to get into subspaces and what a subspace looks like. That's going to lead us into spanning sets and talking about linear independence, which is going to take us to basis and dimension. And then we'll finish up talking about rank and nullity and change of basis. So let's get started. In 401, we're going to review everything we need to remind us about vectors and what vectors are. So remember, a vector is a quantity that has both a magnitude and a direction. Usually we show a vector graphically by an arrow. So we may see a vector that looks something like this. It's got a magnitude and it's got a direction. Magnitude is how long it is. And the direction gives us a place that it's going to. So you can think about directions kind of like cardinal directions, like north, south, east, or west. Notation for vector in this textbook uses a lowercase, and I'm going to put an arrow over it. The book uses a bold letter, but I can't write bold, so I'm going to put a little arrow over it, and that lets us know that we're dealing with a vector. Now we can talk about vectors in 2 dimensions, 3 dimensions, 4 dimensions, and so on. So how long the vector is called the magnitude of the vector. And the magnitude is always the distance from the initial point to the terminal point. So in this case, it would be the distance from here to here. The arrowhead represents the direction. So in this case, this is going to the, I would call that northeast direction. And when we talk more about vectors, we could actually talk about that angle in between here, but we'll get to that later. The zero vector is a special vector. It's a vector that has a magnitude of 0, which means that it has a length of 0, and there is no direction for the zero vector. We say 2 vectors are equal if they have the same magnitude and the same direction. So we can pick vectors up and we can move them anywhere on the xy plane, but as long as they have the same magnitude and direction, then we say that they are going to be equal to each other. So those 2 vectors have the same magnitude and direction. So they are equivalent vectors. They're vectors that are equal. Now, if a vector starts at the origin, it's called a position vector. So when we add vectors, we can add them algebraically and geometrically. Geometrically, we're adding them tip to tail. So if we're adding vectors v plus w, then we're going to place vector v on our Cartesian plane. And then to get to w, we are going to start at the end of v and then draw w. The sum vector starts where v starts and ends where w ends. So let's look at an example of that. Suppose we want to add the vectors 3, 2, and -4, 5. So let's add these 2, and I've got a Cartesian plane here that'll help us do that. So the vector 3, 2, I'm going to draw that as a position vector. We're going to do v plus w, by the way. So v2 is going to move over 3 and then up 2. So here's our vector v. W is going to move -4, 5. So I'm going to treat where v ends kind of like a pseudo origin, and then I'm going to move left 4 and then up 5. So there's my w. V is going in a northeast direction. W is going in a northwest direction. So that sum, V plus W, would start where V starts and end where W ends. So our sum, and I will do that in green, will start here at V and end up here at W. So there's our sum, V plus W. Now, algebraically, if we were to add those, we just add the x components and then the y components. So 3 minus 4 would be a negative 1. 2 plus 5 would be a 7. So that would be our sum vector algebraically. That green vector would be the sum vector geometrically. Now, these should represent the same vector. So if I start at V and I end up at this terminal point here, how did I get there? This should tell me how I got there. Well, from V, I should go negative 1 units. So I should go 1 unit to the left and then up 7. And as you can see, that's exactly what happens to get to that terminal point up here in that region. So let's do another one. Let's say V is equal to negative 2, negative 3, and W is equal to 4, negative 1. So V is negative 2, negative 3. I'm going to start at the origin to draw V. And then W is going to start where V ends, and then we're going to move. So this is going to move 4 to the right and down 1. So there's my W. So my sum vector starts where V starts and ends where W ends. So there's my sum, V plus W. Now, if I were to add these two vectors together algebraically, I just add like components. Negative 2 plus 4 is a 2. Negative 3 plus negative 1 is a negative 4. Now, this also tells me how I got there. So I started here for that brown vector, and I ended up here. How did I get there? Well, from the starting point, I moved 2 to the right, and then I moved 4 down. So that's giving me that direction on how to get there. You can think about it kind of like a road map. So that's how we add vectors algebraically or geometrically. And we could do the same thing in 2 dimensions or 3 dimensions, although it would be difficult to draw on 3 dimensions. When we talk about the properties of vector addition and scalar multiplication, vector addition is always going to be closed for one thing under addition. And what that means is if I take a vector that's in 2 dimensions and I add another vector that's in 2 dimensions, I will still get a vector that's in 2 dimensions. If I add a 3-dimensional vector to a 3-dimensional vector, I will get a 3-dimensional vector. There's no way you can get anything that's outside of that world that U and V come from. That's what it means to be closed under addition. The commutative property also holds, which means I can add vectors in any order and I'm going to get the same vector regardless. Associative property for addition holds. I can change the groupings. I can group U plus V and then add W, or I can group V plus W and then add U. I will get the same thing regardless. I have a zero vector, which is called an additive identity. So that if I take any vector and I add the zero vector to it, I will get that vector back. 5 gives us an additive inverse. If I take U and I add its negative, I'll get the zero vector back. So for instance, if I let U be the vector 2, 3, then negative U would be negative 2, negative 3. So if I add u plus its negative, I will get that identity vector back, which is the 0 vector. The next few deal with scalars. So in 6, we have a scalar c times a vector u. If we multiply those, then we're going to get a vector. So what this is saying is if we have a scalar c, let's say we have a 2-dimensional vector u, then a scalar times a 2-dimensional vector will still be a 2-dimensional vector. So that's called closure under scalar multiplication. We get something that lives in the same world that we started in. Same thing would be true with 3-dimensional vectors. If we have a scalar value, so think about a scalar as a real number, times a 3-dimensional vector, then I will still get a 3-dimensional vector. So I started in the 3-dimensional world with u, I end up in the 3-dimensional world. There's no way I can get out of that 3-dimensional world. So that's what it means to be closed under scalar multiplication. Then we have a couple of distributive properties. If c is a scalar, and I need the scalar c times the sum of uv, I can distribute that scalar in and get the same value by taking c times vector u plus c times vector v. The second distributive property talks about the sum of two scalars multiplied by a vector. So if I have c plus d, where c and d are both scalars, multiplied by vector u, I can think about distributing this way. So I have c times vector u plus d times vector u. None is an associative property for multiplication. So I have c times du, where c and d are scalars. That's the same thing as if I group c and d together first, and then I multiply that scalar value by vector u. And then 10 is about the multiplicative identity. And 1 is our multiplicative identity under the rules. So if I take 1 times any vector, I'm going to get that vector back. Theorem 4.3 is about properties of the additive identity and the additive inverse. So we're going to let v be some vector in Rn. So let's just talk a minute about that notation before we proceed. So Rn means nth dimensional space. So if we're in R2, we're talking about 2 dimensions. If we are in R3, then we are talking about 3 dimensions. And if we're in R4, then you guessed it, that would be 4 dimensions. So these properties actually hold for any dimension, which is kind of cool to think about that it's been generalized that way. So we have a vector that's in Rn, and we're going to let c be a scalar. Then the following properties are going to hold. The additive identity is going to be unique. So that is, if we take v plus u and we get vector v back, then this v is going to be equal to the 0 vector. And remember, it's the 0 vector in Rn. So if it's in 2 dimensions, my 0 vector is 0, 0. If it's in 3 dimensions, it's 0, 0, 0, and so on. But it has to be unique, which means that there's only one 0 vector that could ever work for that. 2 is about the additive inverse. And it says that it also has to be unique. So if I were to take vector v and I add its inverse u and I get 0, then the only way that can happen to get that 0 vector is if u is equal to the inverse of v. So what this is saying is that there's only one inverse that exists for each vector in Rn. Three is about the scalar 0. If I take 0 and I multiply by any vector in Rn, I'm going to get the 0 vector. Now notice the notation here. This 0 is not bolded. The V is, so V is talking about a vector. This 0 is bolded, which means I'm talking about the 0 vector. Four is about the 0 vector. If I take a scalar C, any number, any real number, times the 0 vector in Rn, I will get the 0 vector. Again, notice the notation. There's a very subtle difference here. Notice that those are bolded zeros. That means that they're talking about a vector, not just a number. 5. If I have C times V is equal to 0, the only way that can happen, and remember this is the 0 vector, the only way that can happen is if either this scalar is C or I started with the 0 vector to begin with. And then 6, if I take the negative of vector V, then I get vector V back. So these seem like they are simple properties, and that's because we've always dealt with the real numbers, and our additive identity has always been 0, and our multiplicative identity has always been 1. So what we're going to do in the next section or two is we are going to kind of rock things around a little bit and say, well, what if we change the definition of something like addition and multiplication that we've taken for granted so long? How does that affect all of these different axioms, and what happens then? So stay tuned for some fun times coming up. So just to review a few more things about vectors before we finish this review section. When we talk about a scalar, we're talking about a quantity that only has a magnitude. When we talk about the magnitude of a vector, we can use this, it looks like a double absolute value. That's representing the notation for a magnitude of a vector. And remember, magnitude is how long something is. So to find the magnitude of a vector that's in 2 dimensions, it's the square root of the first value squared plus the second value squared. In 3 dimensions, it would be the value of the first squared plus the second squared plus the third squared. And all of this is built around the idea of that position vector. Which means that it's starting at the origin. So for example, if I have a vector, let's go 2 dimensions, 2, 1, and I need to know the magnitude. The magnitude would be the square root of 2 squared plus 1 squared, which would be the square root of 5. So that's how long that vector is. So here's my vector. That's how long it is from the origin to the point 2, 1. It's square root of 5 units. When we talk about magnitude properties, magnitude's a distance, is how long something is. So distances always have to be positive. So that magnitude's always going to be greater than or equal to 0. Now the only way it can be equal to 0 is if we start with the 0 vector to begin with. So that's IF. F means if and only if. So that's a theorem that works both ways. And what this is saying is backwards is that if the vector is a 0 vector, then the length is going to be 0. That third property says if we were to take the magnitude of negative v, then that's going to be equivalent to the magnitude of v. So remember, negative v is the same vector in a different direction. So if we have the vector, I'm going back to 2, 1 here. We said that magnitude was square root of 5. Well, if we were to look at negative v, that vector would be negative 2, negative 1. So that vector would look like this. So it's the same vector, It's just going in a different direction now. That negative just changes the direction on the Cartesian plane for that. But the magnitude is still going to be the same. So if I were to take the magnitude, it would be negative 2 squared plus negative 1 squared, which would still be the square root of 5. And then that last one, if we were to take the magnitude of a scalar times v, that's equal to the absolute value of the scalar times the magnitude of v. So let's look at an example. Suppose we wanted to know the magnitude of negative 3v. And we're still going to use that v is equal to 2, 1. So if we wanted to know what is that, well, that would be equivalent to taking the absolute value of negative 3 times the magnitude of v. And our magnitude of v was square root of 5. So we're going to have 3 square root of 5 for that answer. Now, if we would have done that the long way, negative 3v in our case would be negative 6, negative 3. So take the magnitude, negative 6 squared plus negative 3 squared. So that's going to be 36 plus 9, which is 45. So 45 is the same thing as 9 times 5, which is 3 square root of 5. So you're going to get the same answer either way. So it's just showing that that works. So now we need to talk about what a unit vector is. Unit vectors are vectors that have a magnitude of 1. So to find a unit vector, it's going to be 1 over the magnitude of v times a vector v. So if we wanted a unit vector for this vector v, we said the magnitude earlier was square root of 5. So our unit vector would be 2 over square root of 5 times 1 over square root of 5. Not times, sorry, comma, 1 over square root of 5. So that unit vector will go in the same direction as v, but the length of that vector is 1. And we could always double check that length if we wanted to. But that's always going to happen. Unit vectors have nice properties that we will talk about later in the course. An algebraic vector v is equal to, and this is called component form of AB, is represented as C, where A and B are row numbers and are called components of V. There's a typo right here. Let me correct that. That sentence didn't make any sense at all. So an algebraic vector is a vector where A and B are the components. So A and B are row numbers and are called components of V. So we're talking about these values in here. And like I said, that's called the component form of a vector. Now, if this vector starts at the origin, so that's the initial point, then we call this guy a position vector. And that terminal point is some other point in space. So if we have 2 points in space, and we have a vector between those 2 points, we can pick that vector up literally and we can move it to start at the origin, and we can find what's called its position vector. And to find that, it's always going to be the terminal point minus the initial point. So for example, let's do this on our Cartesian plane, going back here. Let's say we had points 3, 2, and -4, 5. So here's the point 3, 2. And here's the point -4, 5. So we're going to say this is the initial point. So we have a vector that's starting at 3, 2 and ending at -2, 5. -4, 5. So this vector would look something like this. So to find the position vector, remember it's terminal minus initial. So it's going to be -4 minus 3, and then 5 minus 2 for the components. So we're going to have -7, 3. Now, this vector will look just like this vector in space, only it's going to start at the origin instead. So if I were to graph this vector here, that position vector, I would go -7 to the, so I'd go 7 to the left, and then up 3. So you can see how it's that same vector. We have literally just picked it up and moved it to the origin. It's still going in the same direction. Everything's the same. Two vectors, v and w, are equal if and only if their corresponding parts are equal. And that will help us solve little vector equations. So suppose we had something like this, where we had vector v. Oh, let's not even do that. So what that property is saying is that for this vector to be equal to this vector, all the components have to be the same. So you see the front components are the same, the last are the same. So the only way this can be equal is if those middles are the same. So that tells us x is going to be equal to 2. So that's an equality property. And then we can talk about those unit vectors I and j. Now we're talking in 2 dimensions. We know in 3 dimensions we have I, j, and k. So we're going to let I be the unit vector along the positive x-axis. So that unit vector is the vector 1, 0. J is the unit vector along the positive y-axis. So j is equal to the vector 0, 1. So we can take any vector and we can write it as a linear combination of those unit vectors, where A is the horizontal component and B is the vertical component. So let's look at an example there. Let's say we have the vector 2, 7. So we can write this, it's kind of an expanded form. So we can think about this in terms of I and j, and we can write it in terms of that I and j notation. Algebraically, this guy is equivalent to that, and that 1, 0 is our I vector, that 0, 1 is our j vector, and those are called unit vectors. So those are like our normal unit vectors. Anything we can do in 2 dimensions, we can do in higher dimensions. So let's say we have a 3-dimensional vector. So we could rewrite this in terms of the unit vector 1, 0, 0, the unit vector 0, 1, 0, and the unit vector 0, 0, 1. So we could write it this way. So we use I, J, and K here. Anything above 3 dimensions, we can't really use I, J, K. So that's where you start seeing like E1, E2, E3. So let's say we had a 4-dimensional vector and we wanted to write it in this expanded form. So we could call this E1. We could call this E2. That's the typical notation that you see for higher dimensions. E3. And then E4. And so on. Now, IJ, IJK, E1, E2, E3, E4. Notice that they're unit vectors, so they have a length of 1. Unit vectors are not unique. This actually forms something called a basis, which means that we can write any vector in 2 dimensions in terms of I and J. We can write any vector in 3 dimensions in terms of I, J, and K. But those vectors, which, like I said, forms a basis, bases are not unique to the spaces 2 dimensions or 3 dimensions. And we'll talk more about that later in the course. Later in this chapter, actually. It's kind of cool. So we've talked about how to find magnitude in a unit vector and how to add and subtract algebraically. So now we need to kind of refresh this idea of linear combinations. We can take vectors and write them as linear combinations of other vectors. And that's exactly what we did over here with these 3 vectors. We wrote them as linear combinations of those unit vectors, I and J, or I, J, and K. So I want to do another example with linear combinations. So we're going to want to write vector v as a linear combination of u and w, if possible, where u is the vector 1, 2, and w is the vector 1, negative 1. So here's our v. We're using the vector 2, 1. When we talk about linear combinations, we're talking about what's the value of the scalar. So we want v to equal some number times u plus another number times w. So our v is 2, 1. We want that to equal a times vector u plus b times vector w. So this is going to give us a system of equations that we need to solve. So I'm going to multiply through. So 2, 1 is going to be equal to a 2a plus b negative b. So those first components gives us an equation. 2 has to be equal to a plus b. And then the last components gives us another equation. So now we've got this system that we want to solve. going to do RREF. And we're going to see if there's a solution to this. And it turns out this one does have a solution, and there's a unique solution. So what this is saying is that if A is 1 and B is 1, then we'll get that vector. So then our final answer, and I'll write this in a different color so it stands out. So that vector 2, 1 can be found by taking 1 times vector u plus 1 times vector v. So those are the scalars that we found. Linear combinations is going to be a really important part of this course, and we're going to see that a lot, especially in this chapter.